Morning to one and all. In this class, we are going to discuss about losses of a DC machine and efficiency of a DC machine. First of all, what are the different losses of a DC machine? So here we have the table ma. So in this table, total losses in a DC machine. So the total losses in a DC machine are three types more. One is copper losses, iron losses, mechanical losses. So again, copper losses are further classified into three types. One is armature copper loss, shunt field copper loss, and series field copper loss. Coming to iron losses, hysteresis loss and eddy current loss. So mechanical losses are two types more. One is frictional loss, another one is windage loss. Okay, so these are the total losses in a DC machine. DC machine means maybe generator or motor. Okay, first of all, the various losses in a DC machine, whether it is generator or motor, classified into three types now. Okay, number one, copper losses. So first of all, what is copper loss? So why we call this type of losses copper losses? The copper losses are the losses due to current flowing in a copper winding. Actually, the copper losses are the losses due to current flowing in a copper winding. When current flows through copper winding, there will be some losses. So these losses are called copper losses. Okay. Next, the copper losses are proportional to square of current. The copper losses are proportional to square of current, and copper losses are further classified into three types more. One is armature copper loss, shunt field copper loss, and series field copper loss. Okay, so armature copper loss. Coming to armature copper loss, IA square RA. Armature copper losses are IA square RA. IA means armature current. When armature current flows through armature resistance, we get armature copper losses IA square RA. Okay, so the copper loss when current flows through armature winding is called armature copper loss. And shunt field copper loss, the copper loss when current flows through shunt field winding, this is shunt field copper loss. Next, series field copper loss, the copper loss when current flows through series field winding. Okay, so armature copper loss means the current when flows through armature winding, the losses will occur. These losses are armature copper loss. The losses when current flows through shunt field winding, we get shunt field copper losses. These are also called ISH square RSH loss. Okay, and series field copper loss. So the losses due to current when flows through the series field winding is called series field copper loss. Okay, these are all copper losses. So what is copper loss? The current when flows through any copper winding, there will be some loss. That loss is called copper loss. Simply we call IA square RA loss. Next, so here one important point, brush contact loss. Brush contact loss is directly proportional to armature current IA. This loss also induced in copper losses. So the brush contact loss is also included in copper loss or related to copper loss. The second type of loss, iron or core losses. Iron losses are also called core losses. These losses are also called magnetic losses or core losses. Why? Because these losses occur due to these losses occur in core, in magnetic core. Okay, that's why these are called either magnetic loss or core losses. So these losses are also called magnetic losses. These include hysteresis loss and eddy current loss. So iron losses are two types now: hysteresis loss and eddy current loss. So let me see what is hysteresis loss and what is eddy current loss. Coming to hysteresis loss. The hysteresis loss is proportional to the frequency and the maximum flux density. So the hysteresis loss is directly proportional to maximum flux density and frequency. So here we have the equation for hysteresis loss, that is, so this is a hysteresis coefficient into V maximum power 1.6 means flux density, maximum flux density per power 1.6 into F. F means frequency, V is the volume of the core in meter cubed. Okay, so hysteresis loss is equals to V maximum power 1.6 into frequency into volume in watts. Okay, so this is the power loss now. This equation shows the power loss due to hysteresis. Okay, the loss is basically due to reversal of magnetization of the armature core. So reversal of magnetization process valla so manaku konta loss vastundi. So that loss is called hysteresis loss. Next, the hysteresis loss is minimized by selecting the core material having low hysteresis coefficient. Actually, hysteresis loss can be reduced with the help of low hysteresis coefficient material like silicon steel. Silicon steel is having low hysteresis coefficient now. So that's why always we preferred silicon steel material for, in transformer laminations or in generator core laminations. And coming to other iron loss, that is eddy current loss. The eddy current loss exists due to eddy currents. So this loss is due to eddy currents. When armature core rotates, it cuts the magnetic flux and EMF induced. So actually, when we give uh, mechanical energy to the DC machine, DC machine starts to rotate. So in DC machine, armature starts to rotate. When armature core starts to rotate, the flux cut takes place in armature winding as well as core. Core is also made with conducting material. The core is also made with conducting material like silicon steel. Silicon steel is also a conducting material. So when flux cut takes place with the armature winding, the EMF induced in the armature winding. Okay, it is actually so everybody know. But at the same time, the armature core also cuts the flux. So when core cuts the flux, EMF induced in the armature core. This EMF is called eddy eddy current EMF. So or due to this EMF, the current will produce it. This current is called eddy current. So when flux cut takes place, an EMF induced in the core. The laminated part is this. The laminated part or the laminated structure is a closed path now. So when there is a closed path, the voltage or the EMF converts into current. This current is called eddy current. So how to reduce the eddy current? The eddy current loss is minimized by selecting the laminated construction. So why we used laminated construction instead of a single core piece. So why we prefer laminated structures in transformers, in generators again in armature core and in field poles. Okay, so uh, whatever the iron core, so always preferred laminated structure mark. Why? Because uh, as minimum as possible. So when we maintain as minimum as possible losses, we get high efficiency or more efficiency. Eddy current loss formula is equals to K into K is the constant mark, B maximum square, F square, T square, V watts. Okay, so K is the constant, B maximum with maximum flux density, and F is the frequency, T is the thickness of lamination, lamination యొక్క thickness, and V is the volume of the core. The eddy current loss is minimized by selecting the laminated construction of the core. Iron losses are always constant. Remember, iron losses are always constant, whatever be the load. These iron losses are independent of load small. If load is 0, or if load is half, or if load is full, whatever be the load, the losses are always constant. No change in uh, mechanical loss, sorry, no change in eddy current loss and no change in hysteresis loss. The third loss, mechanical loss. These losses are two types. One is friction losses, another one is windage losses. Coming to friction losses, how the friction losses are occur? The loss due to friction between shaft and bearings. So actually, the bearings are provided over the shaft for smooth rotation. So in between these two, there will be some friction. The loss due to friction, there will be some loss due to friction. Okay, so the loss due to friction between shaft and bearings is called friction loss. Okay, next, windage loss. Coming to windage loss, the loss due to air resistance. Actually, the core pushes the air, or the core always rotates uh, after I mean it always rotates by pushing the air inside the generator. So the loss due to air resistance. So air also opposes the rotation of the armature. So this opposition or this friction is called windage loss. So these losses are constant, just like iron losses. Mechanical losses are also constant losses. Okay, so in these three, important losses, so coming to table, so in these three important losses, copper losses, iron losses, mechanical losses, in these three, copper losses are always variable. When load increases, copper losses increases. When load decreases, copper losses decreases. When load is zero, copper losses are almost zero. Okay, but coming to iron losses, whatever be the load, the iron losses are always constant. When you start the motor or when you start the machine, the losses come present in the machine. These are always constant. Mechanical losses. Mechanical losses are also constant. Frictional losses and windage losses are the mechanical losses. These two are also constant. Mechanical losses are constant losses. Iron losses are constant losses. Copper losses, coming to copper losses, armature copper loss, shunt field copper loss, series field copper. In these three, armature copper loss and series field copper loss, both are variable. Only shunt field copper loss is constant. Okay, so overall copper losses are variable losses. Okay, So this is the matter about losses in a DC machine. Coming to power flow diagram in generator as well as in motor. Total losses is equals to in any mission total losses is equals to constant losses plus variable losses. Okay, so constant losses means mechanical losses and iron losses. Variable losses means copper losses. Power flow in a DC generator. Let me see how the power starts and how it ends. Let me see in the form of block diagram. So this is the power input. So what's the input to the generator? Mechanical power or rotational power. So when we give mechanical power input to the generator, first there will be iron and friction losses. So mechanical power మనం ఇచ్చిన వెంటనే సో షాఫ్ట్ కు బేరింగ్ కు మధ్యలో కొన్ని లాసెస్ ఉంటాయమ్మా, ఆ లాసెస్ ఐరన్ అండ్ ఫ్రిక్షన్ లాసెస్. సో ఈ మెకానికల్ పవర్ ఇన్పుట్, when we give mechanical power input, next the iron and friction losses are occur. So mechanical power input minus iron and friction losses, we get electrical power developed in a armature. Electrical power developed in a armature, EGIA, EG into IA, called electrical power developed in the armature. Next after this, copper losses. When current flows through the copper winding, there will be copper loss. Okay, so electrical power developed in a DC machine minus copper loss, we get electrical power output. Generator lo input వచ్చేసి mechanical energy, output వచ్చేసి electrical energy. So when we give mechanical energy, there will be iron and friction losses first. After that we get electrical power developed, EGIA. So after that we get electrical power output, VI. This is the power output, generator output. Okay, coming to power flow in DC motor. So the power flow in DC motor is exactly reversible to power flow in a generator. When you observe, so here output is electrical input, but in motor input is electrical input. When we switch on the supply, so the power flows through the generators winding, and power developed inside the armature, and due to force the armature starts to rotate and we get mechanical energy. So here the electrical input is the electrical power is the input. So when we give electrical power, first there will be copper loss. So why? Because when we give the electrical input, the current flows through the winding. When current flows through the winding, so there will be copper loss. So electrical power input minus copper loss, so we get power developed in the armature, that is EBIA. Power developed in the armature is EBIA. So power developed in the armature minus iron and friction loss, iron and friction loss, we get motor output. Motor output is in the form of rotational power or rotational energy, లేదా దాన్ని మనం సింపుల్ గా మెకానికల్ అవుట్పుట్ అంటాము. ఓకే, సో జనరేటర్ లో ఏం జరుగుతుంది? సో వెన్ వి గివ్ రొటేషనల్ ఎనర్జీ, ఫస్ట్ దెర్ విల్ బి సమ్ ఐరన్ అండ్ ఫ్రిక్షన్ లాసెస్. సో మెకానికల్ ఇన్పుట్ లో నుంచి ఐరన్ అండ్ ఫ్రిక్షన్ లాసెస్ తీసేస్తే వి గెట్ నెట్ పవర్ డెవలప్డ్ ఇన్ ద ఆర్మేచర్, ఈజీఐఏ. ఈజీఐఏ మైనస్ కాపర్ లాసెస్, తర్వాత నెక్స్ట్ కాపర్ లాసెస్ వస్తాయి. సో EGIA minus copper losses, we get the power output VI, so which is available at terminals. Okay, next coming to DC motor. In DC motor, we will give electrical power as input. When we give electrical power as input, so there will be some copper losses and there will be some iron and friction losses. So first, when we give electrical power input, first uh, there is a chance of copper losses. Electrical power input minus copper losses, we get power developed EBIA. EBIA minus iron and friction losses, we get rotational energy or mechanical output. Mechanical output. So we can also call motor output. Okay. So this is the matter about block diagrams of power flow in a DC generator and power flow in a DC motor with the help of block diagrams. Next, when you know or when you study these two block diagrams, it is easy to calculate efficiencies of a DC machine. Okay, in case of DC generator, the following three efficiencies are defined. So DC generator అయితే efficiencies ని మనం ఎలా ఆ formulas ని ఎలా derive చేయొచ్చో చూద్దాం. First of all, mechanical efficiency. Mechanical efficiency is equals to EGIA by P input. ఇది P suffix input ma. Okay, P suffix in. So EGIA is the power developed in a armature by input power into 100. Okay, so DC machine kadam. So sorry, generator kadam. So this is the generator. Okay, so in this generator, what we need to derive mechanical efficiency. Mechanical efficiency is this one, ma. EGIA, power developed in a armature by mechanical input. Power developed in a armature by mechanical input waste, we get mechanical efficiency. Next, electrical efficiency. So VI, output by electrical power developed is the input. చూడండి ఈ బ్లాక్ ఇన్పుట్ ఏమో electrical power developed. So this is the input and this is the output. And what's the formula for frequency? What's the formula for efficiency? Output by input into 100. Okay, so this is the output for electrical efficiency and this is the input. So output by input means electrical power output by electrical power developed into 100, we get electrical efficiency. So what about mechanical efficiency with the help of block diagram? Here in this block diagram, this is the mechanical input and this is the output. So only compared to these two, only when compared to these two, this is the input and this is the output. Mechanical power minus mechanical input minus iron and friction losses, we get output, that is power developed. Okay, so output by input, electrical power developed EGIA by mechanical input, we get mechanical efficiency. Sare, inkokati overall efficiency of the machine. So ఇక్కడ ఓవరాల్ ఎఫిషియన్సీ తీసుకోవాలంటే ఈ మొత్తం ఎంటైర్ బ్లాక్ చూడండి. సో ఇందులో దిస్ ఈస్ ద ఇన్పుట్ అండ్ దిస్ ఈస్ ద ఓవరాల్ అవుట్పుట్. ఓవరాల్ ఎఫిషియన్సీ అన్నప్పుడు అవుట్పుట్ బై ఇన్పుట్. సో అవుట్పుట్ ఏమో ఇక్కడ ఎలక్ట్రికల్ పవర్ అవుట్పుట్ VI, ఇన్పుట్ మెకానికల్ పవర్ ఇన్పుట్ is the input. Okay, so P in is the input power, P out is the output power. ఇక్కడ అవుట్పుట్ ఏది అంటే ఎలక్ట్రికల్ పవర్ అవుట్పుట్ VI, ఇన్పుట్ ఏది అంటే P ఇన్పుట్. ఓకే, ఓవరాల్ ఎఫిషియన్సీ. సో దిస్ ఈస్ ద రేషియో ఆఫ్ total power supplied to total mechanical power input to the generator. P out by P in. P out అంటే VIL. తర్వాత ఇన్పుట్ పవర్, వీ డోంట్ నో మెకానికల్ ఇన్పుట్. మెకానికల్ ఇన్పుట్ను మనం ఎప్పుడు క్యాలిక్యులేట్ చేయలేము. సో అందుకే మెకానికల్ ఇన్పుట్ను డైరెక్ట్గా P ఇన్పుట్ అని వేస్తాం. ఓకే, సో These are the efficiency formulas. One is mechanical efficiency of a DC generator, electrical efficiency of a DC generator, overall efficiency of a DC generator. So how you derive? Very easy one. So in this block diagram, overall when you if you want mechanical efficiency, this is the input and this is the output. So when we compare these two, output by input, so output EGIA by input P input, power input, okay, or mechanical input. Next, electrical efficiency. So this is the input to this block and this is the output. So output by input. Output by input means VI by EGIA. VI by EGIA. So finally we get output power. Okay. Next, power flow in a DC motor. So already you know how to derive the efficiency equations in DC generator or DC motor. So coming to DC motor, so in the same way here also, based on block diagram, it is very easy to derive the equations. First of all, mechanical efficiency. The first one is mechanical efficiency. See, this is electrical input, ma. This is output. This is electrical input. This is electrical output. Output by input means EBIA by VI. EBIA by VI. We get electrical efficiency of a motor. And mechanical efficiency, motor output by power developed. Motor output by power developed. P out by EBIA. Just we get mechanical power. And what is the overall efficiency of a motor? Overall efficiency of motor is electrical input, mechanical output. So what's the formula for efficiency? Output by input. Output, motor output, P out by input VI. Electrical power input VI into 100. We get efficiency, overall efficiency of the DC motor. Okay. Next, so this is the general formula for efficiency. If you take a generator, or if you take motor, if you take a transformer, synchronous machine, as your wish. If you take any machine, the formula for efficiency is output by input. The general formula means output by input. But we can also write the efficiency formula output by output plus losses. So why? Because output input is equals to output plus losses. So ఏదైనా ఒక మెషిన్ కు మనం కొంత పవర్ ఇచ్చినప్పుడు అందులో నుంచి మనకు కొంత అవుట్పుట్ వస్తుంది. సో వాట్ అబౌట్ రిమైనింగ్ ఈజ్ ఇన్ ద ఫార్మ్ ఆఫ్ లాస్. ఓకే, సో ఇప్పుడు మనం టోటల్ ఇన్పుట్ కావాలనుకుంటే ఏం చేయాలి? వచ్చిన అవుట్పుట్ ప్లస్ లాసెస్ ఆ రెండు యాడ్ చేస్తే దట్ ఈస్ ఈక్వల్ టు ఇన్పుట్. సో హియర్ ఆల్సో efficiency of a generator is equals to output by output plus losses. Generator లో అవుట్పుట్ తెలుస్తుంది మనకు, ఇన్పుట్ తెలియదు. చూడండి, జనరేటర్ లో మనం ఏమి ఇస్తున్నామా? మెకానికల్ ఇన్పుట్ ఇస్తున్నాం, రొటేషనల్ ఎనర్జీ ఇస్తున్నాం. రొటేషన్, వి కాంట్ క్యాల్కులేట్ రొటేషనల్ ఎనర్జీ. ఓకే, సో రొటేషనల్ ఎనర్జీ ఇస్తున్నాం. తర్వాత మనకి అవుట్పుట్ ఏమొస్తుంది? జనరేటర్ లో ఎలక్ట్రికల్ అవుట్పుట్ వస్తుంది. ఇట్ ఈస్ ఈజీ టు క్యాలిక్యులేట్ ఎలక్ట్రికల్ అవుట్పుట్ when you know V and I at terminal V and I. So the product of V into I is equals to output. If you know output and if you know losses, it is easy to calculate generator efficiency. So with the help of this formula. So output by output plus losses. Here we don't know what's the input. Generator కు మెకానికల్ ఇన్పుట్ ఉంటుంది మా ఆ మెకానికల్ ఇన్పుట్ ను మనం క్యాలిక్యులేట్ చేయలేము కాబట్టి మనకు ఉన్నది ఏంటి అవుట్పుట్ తెలుసు. So with the help of losses, we are going to calculate the efficiency with this formula. So output by input, actual formula output by input. Ikkada input is equals to output plus losses. Okay. So output by output plus losses into 100 for generator. Coming to motor. So motor lo input తెలుసు మనకు అంటే ఎలక్ట్రికల్ ఇన్పుట్ కాబట్టి సో we know input. సో ఇన్పుట్ తెలుసు కాబట్టి ఇన్పుట్ తెలుసు లాసెస్ తెలుసు మాకు సో హౌ టు క్యాలిక్యులేట్ ద ఎఫిషియన్సీ ఇన్ మోటార్ ఇన్పుట్ మైనస్ లాసెస్ మీన్స్ అవుట్పుట్ మాకు ఓకే సో ఇన్పుట్ మైనస్ లాసెస్ బై ఇన్పుట్ ఇంటూ 100 సో ఇన్పుట్ మైనస్ లాసెస్ ఇస్ ఈక్వల్స్ టు అవుట్పుట్ బై ఇన్పుట్ ఇంటూ 100 ఫర్ మోటార్ సో దిస్ ఇస్ ద మ్యాటర్ అబౌట్ losses in a DC machine. And in these losses, three types of losses: copper losses, iron losses, and mechanical losses. Mechanical losses and iron losses are constant losses. In copper loss, only centrifugal loss is only constant loss, remaining all variable losses. Okay, and so this is the formula for efficiency. So efficiency is equals to output by input. So we can also write this formula output by output plus losses in generator, input minus losses by input in motor. Okay.